Hello and welcome to another exciting lecture for stats. In this lecture we'll be going over distributions of data. And before I get into it, let me just say that I said this in the homework review, but if you didn't watch the homework review, then I need to say it again. But I think all of you are really on the ball. You're there with it. I don't see any indications that anybody is struggling or having issues. So because of that, I'm going to go slightly faster when giving these lectures just to keep you from being bored. But if I do go too fast, please email me, message me, let me know so that I can slow down. I don't want anybody to be left behind, but at the same time, if I don't need to spend too much time on this, I don't want to waste your time with going over things in too much detail. As I said, we're going to be looking at distributions of data in this set of slides. Let's get into that. So the first thing, when we talk about distributions of data and we're looking at why we do statistics and why we do a lot of the things we do, well, we can look at this slide and now we look at this over here. We're given this data. And this is actually only 23 individuals where the data is collected on, but we've got an ID variable here. We've got a nominal variable, their gender. We've got a continuous variable, age. We've got another nominal variable, ethnicity. We got a variable that was possibly done research on, sensitivity. It could be sensitivity to various different things, which is typically going to be at least a ordinal level variable. Likely it will be treated as a ratio level variable. But when we look at these and we ask, okay, well, what's the average age of this group? You can look through this age variable and kind of get an idea. Well, most of the people are 21, 20, 22 in that range. You got a couple people who are a bit older, 39, 47, 32, 34. That one that's 47 may end up being an outlier, which we'll come back to. But the point here is that we can look at this and tell maybe a range, but we can't really tell too much about the data just looking at it. And again, this is with only 23 people. Now imagine you've got 900 people. Let's say we wanted to know what the average sensitivity score is. Well, again, looking at this, we can see that it ranges from 1 to 6, but where is really the values averaging at? So because of that, we can't just use data in this form and interpret it. It's difficult to interpret, it's difficult to understand, so we need something more effective for organization. And that's what we're going to cover this week, is looking at better ways to organize it. We're going to look at some graphical ways to do it, and then we're going to also include things like the measures of central tendency and measures of variability. So one of the things you can do is exploratory data analysis. This is where you basically arrange and display the numbers to allow you to quickly organize and summarize, as well as interpret the data collected from research. In a sense, what we're doing here is allowing the researcher to take a first look at the data, providing descriptive statistics. However, it can be misleading. So one of the things to keep in mind, even when we get good descriptive statistics, maybe we use graphs, in what it comes down to though is you should still be aware this can be misleading. It's also why we use things like inferential statistics instead of just descriptive statistics when we're doing things, because of this possibility for it being misleading. But really what we're doing here with exploratory data analysis, we're looking at really this first look at the data and descriptive statistics. So what are some things that we can determine? Some things that we can determine are things like the best measure or the single best value to describe the data, or a measure of central tendency. And that's the thing we'll cover in the next set of slides, but a measure of central tendency is one of the things you can get from this. How about how spread out the data is? That's another thing you can get, a measure of dispersion or a measure of variability. And that's what we'll also cover in the next set of slides. You can also from this get a relationship between the variables. We will come actually back to this. We'll come back to this the second to last week of the semester when we look at correlation and regression, but that's where we can look at relationships between variables with this. And then the last thing you can get is the shape of the distribution. And to do that, you have to graph it out. So this set of slides is going to talk about graphing as well as frequency distributions, things like that. That is essentially a way of getting a shape or a general sense of the distribution. So there are multiple methods for data presentation. We're just going to cover a few here. We'll cover bar graph, histogram, frequency curve, and frequency distributions. There's many more than this, stem and leaf plots, other things like that. Those are things that I'm not going to cover in here just because we don't need to spend the time covering things that aren't used that often. We could cover things like pie charts and all of that, but instead we're going to look at the things that are used the most often in the behavioral sciences, and that is, again, bar graphs, histograms, frequency curves, and frequency distributions. Before we get into graphs, let's look at some general rules of graphs. So there's some fundamental characteristics of graphs that we need to follow. Again, this should be reviewed for you, so I'm not going to spend too much time on it. But our graph is going to be drawn at right angles. We're going to label the horizontal axis as X, the vertical axis as right. The horizontal, the X, is going to be our independent variable. If we have one, the Y is going to be our dependent variable if we have one. The X axis should be about 4 to 3 on the Y axis. And when we're looking at this, and I said if you've got a dependent variable, it's the Y. Sometimes the Y can also be things like frequencies or percentages, which we'll come back to when we get to some things like that. But the Y, the X is our independent variable, our variable of interest. If you're doing correlational analysis, you've got two essentially dependent variables. You don't have an independent variable. In that case, the X can be either of your variables. The variables need to be clearly labeled on both the X and Y axis. So let's say we were looking at anxiety's effect on performance. We would label this as anxiety. And we'd have to have them labeled for, let's say we were on a 1 to 7 scale for anxiety, and the performance was a 1 out of 10. So it goes up there. The point is we've got performance there. You need to clearly label your axes. And the graph should contain all information that's needed to understand the data and nothing more beyond that. So what you see here, what's on the graph, it's what's needed, but you shouldn't have anything extra. Let's look at the first type of graph, and that's a bar graph. So bar graphs use rectangular bars, that's what you see here, these rectangular bars, to represent nominal data. That's one of the things we're going to talk about, bar graphs and histograms. The big difference there is bar graphs, because they're representing nominal data, and bar graphs represent nominal, your bars do not touch. You've got a gap between your bars, and you've got that gap between the bars. Because it's a nominal data, it's essentially saying that it's representing categories. These categories are discontinuous. There's no continuous values between them. So in this case, we've got bars that are separated. Their bars are not touching. What we've got here is cars sold, and you see here on the y-axis, you've got f of x. We'll come back to this, but that's frequency. So again, in this case, it's not a dependent variable. it's number sold. So in a sense, that's dependent variable, but it's a dependent variable measured by frequency. So the y-axis can represent values, frequencies, percentage, any of those types of things. And we'll come back to that when we talk about frequency distributions. The other type of graph that we're going to look at here is histograms. Just like a bar graph, so just like a bar graph, it's got squares or rectangles to represent the data. However, this represents either ordinal, interval, or ratio level data. Therefore, because it's quantitative, our bars are touching here. There might be gaps where you've got a 0, but that doesn't mean that they're separated because they're not touching. It basically means for this value or range here, it's a 0. There's nothing in there. So the bars are all touching when they are up against each other. The data you see on the right here is a little bit different than what you see in the graph, because the data you see on the right is actually going to be for grouped variables. And when we get to the end, when we talk about frequency distribution, we'll talk about group frequency distribution and look at that and look at how these groups are together. So when you're doing a histogram, you can do it like it is on the left here, which is different individual values are each ranked and each applied, and then you have the bars touching for that, or you can have it like it is on the right and you can have groups of values, but we will come back to that. And just because as I was already saying, I'm not going to go over this again because I just said it, but the rectangles touch, they can be individual or classes or groups. So the last thing we'll talk about is a frequency curve. I'm not going to spend too much time on this. We'll come back to this actually when we talk about correlation and regression and things like that. But a frequency curve is basically just going to be a line that's drawn between the different points when you're looking at various different types of grouped frequencies. So in this case, this line here that you see on this one, the black line, it's not that accurate, but it gives you an idea of what you would see when you see a frequency curve. Okay, so when you're dealing with graphs, histograms, bar graphs, frequency curves, there's some general rules to follow. As I already said, you use bar graphs for nominal level data, categorical or qualitative variables. You use histograms and frequency curves for ordinal, interval, and ratio level data. For continuous variables, the x-axes on the frequency curve are going to be the midpoints. I didn't say that before, but that is something to note, that when you've got a continuous variable, your values are your midpoints. Whereas if you've got discontinuous, your values are just for that variable. So the next thing we're going to talk about here in this set of slides, and it's pretty much the thing we're going to talk about until the end, is frequency distributions. And frequency distributions are basically going to be a distribution of frequencies or of occurrences. So the number of times a score occurs. You're going to take these values and basically have a x value. Your x value is going to be for each different possible value that your variable can achieve or be. I'll have a visual representation on that on the next slide. If you've got intervals, it's got to be between the upper and lower true limits of the class intervals. But really what we're looking at here is this thing we're going to represent as f of x, and this is going to be the frequency or the number of occurrences for each value of x. So this is the number of each x value. So the number of occurrences for that. I'm going to switch to the next slide so you get a visual representation of that. But you've got this here. You've got your x values, that is each value that your variable of interest can take on. In this instance, your variable of interest can be anywhere from 0 to 10, and all of the values in between. When you're doing a frequency distribution, you need to, the top value should be your highest value that the x value can be. So this one here, the 10, your bottom value should be the lowest value your x value can obtain, and you should include every single value between, even if they're zero frequency. Even if they don't occur, you still include all the values between. Then this column is going to be the frequency, the number of times that value occurs. So 10 occurs twice, 9 occurs twice. Down here, 5 occurs 8 times. 0 occurs once. Important to note that 1 occurs 0 times, but we still have it over here because we include all values between the highest and the lowest point. So this is the first step of our frequency distribution. As you can see here, we're going to have many more steps that we're going to do, but the first and most basic step of a frequency distribution is count the number of occurrences of each level of our variable of interest. So in this case, our variable of interest is the x variable, so it's the frequency for each level of the x variable. The next thing we're going to look at is cumulative frequency. So cumulative frequency is going to be the total frequency of scores below the upper limits of the class level. I'll show what that means on the next one, but it's basically all values at and below that point. So the frequency of all of the x values at and below that point. It's written as cumulative f of x. So that is what we're going to write it as. Let me switch to the next slide so you can see a visual representation of that. So here you've got cumulative f of x, and it's all values at and below that point. So let's start at the bottom. The x value of interest is 0. The frequency is 1. So the frequency of all values at and below that point is 1, because there is 1 at or below 0. The next we'll go to is at 1, and there is none at 1, but at and below 1 there's still this 1 down here, this 1 that's a 0, so we're still at 1. At 2, everything at and below that point, we have 3 plus 0 plus 1, so it's going to be the 3 here plus the 0 here plus the 1 here. We get a total of 4. One way to do it is, the way I'm doing it now, is you take the value at that. So let's look at 3. Everything at and below that point, you have 4, you have 3, you have 0, you have 1. So we add all those together, we get 8. Another way to do it is just to take the value at that point. So let's look at 4 now. The value at that point, which is 6, or the frequency at that point, sorry. The frequency at that point, and just add it to the cumulative frequency from the one below. So 6 plus 8 is 14. From here, 8 plus 14 is 22. 7 plus 22 is 29. All the way up to the 2 at the top plus the 38 here is 40. So the two different ways to do it, you could do it the one way for this x of 10, you could do 2 plus 2 plus 3 plus 4 plus 7 plus 8 plus 6 plus 4 plus 3 plus 0 plus 1 going all the way down. Or you could just take that value and add it to the cumulative frequency at the one step below it. You should also note here an important thing, that the total we have, our total, our n, which is 40, should also equal the total of cumulative f of x. So they should be, those two numbers should be equal. Next thing we're going to add on is relative frequency. So relative frequency is now where we're going to take a proportion or a probability. So we're going to take a proportion of the whole when we're dealing with frequencies. So to convert a frequency into a relative frequency, you take the frequency, the f of x, and divide by our n, by our total. So you take each f of x and divide by n, and you get relative frequency, relative f of x. Let's switch to the next slide and look at that. So now we've got our column for relative f of x. We're going to take each one and take our frequency, so this column, the frequency column, and we're going to divide by our n, our total, which is 40. So this one here is equal to our frequency of there, which is 1, divided by 40. This one is equal to 0 divided by 40. That's easy. This one is equal to 3, the value here, the f of x divided by 40, 4 divided by 40, 6 divided by 40, 8 divided by 40. Again, each of these frequencies, like that one, 7, the frequency, the f of x is 7, divided by our n, which is 40. All the way up to the top where we've got 2 divided by 40 and 2 divided by 40. And that is our relative frequency. I'll come back to this later on why relative frequency is important, but relative frequency is actually more important than frequency. Just keep that in mind and we'll come on back to that. Okay, next is cumulative relative frequency. So just like we took our cumulative frequency and we took everything at and below that point, we take our cumulative relative frequency by taking the relative frequencies at and below that point. So cumulative relative frequency is everything at and below that point. Looking at that here, we've got our cumulative relative frequency. It's everything at and below that point. So this one is going to be at the lowest, it's equal. For the next one, we've got everything at and below that point. So it is going to be that at 1 plus down here. Same with the next one. It's the 0.075 plus 0 plus 0.0025. All of the relative frequencies at and below that point. And just like with cumulative frequency to frequency, cumulative relative frequency, you could just take the relative frequency at that point and add it to the cumulative at the one below. So at this point, we've got 0.150. You can add it to the 0.0200 and you get the 0.350. All the way at the top, you take the 0.050, add it to the 0.950, and you get 1. Important thing to note here, so you do cumulative relative just like you did cumulative frequency at and below that point, but for relative frequency, if you add all of them together, you should get something pretty close to 1.000. Rounding may affect this. You may be at 0.998, 1.002, things like that. Rounding may affect it, but you should be pretty close to 1. And when you're drawing this out, just write 1 there, because technically, if you fix the rounding errors, it does come to 1. The same is true with the top line of the cumulative relative frequency. Just like the top line of the cumulative frequency was the same as the n, the top line of the cumulative relative frequency is also going to be 1, which is the same as the bottom line of the relative frequency when all of the relative frequencies are added together. And since the cumulative relative frequency at the top is all of them added together, it makes sense that it's the same as the bottom when all of them are added together. Last thing we're going to talk about is percent. Percent is very simple. Percent, you just take your relative frequency and multiply by 100, and this gives us a percent. Percent is important just like relative frequency. The nice thing with percent is it puts it into terms that the mind is easier able to understand. We can understand certain things better. Those relative frequencies we looked at before, those 0.0025, what does that mean? Well, when we convert it to a percent, you can say, well, that's a percentage of the whole. So we've got this percent column now. we took the relative frequency column, multiplied by 100, and get the percent column. So 0.0025 becomes 2.5. That means 2.5% of the whole has a value of 0. Up here you get the 0.200, it becomes 20%. That means 20% of the values in the data set have a value of 5. All the way up to the top with the 0.050, that becomes 5%. If you add all these together, you should get 100%, just like if the adding here, you get 1.00, you take 1 and multiply by 100, and you get that 100. Percent is easy to get to, shouldn't be any hassle with that. And then of course you have to do cumulative percent, just like we did cumulative with the others. So everything at and below that point, cumulative percent. So there's two ways to do this. You can take and do everything at and below that point for percentage. So we've got here, that's 2.5 at and below this point. This one is going to be this one plus this one. This one's the 10 here is the 7.5 plus 0 plus 2.5. Or easier, simpler way to do it, just take your cumulative relative frequency and multiply by 100 to get your cumulative percent. So 0.025 times 100 is 2.5. 0.550 times 100 is 55%. So you can see here, good thing to look at, 55% of the values are going to be at and below 5. And that's a good thing to know if you wanted to say, okay, well, half of the values are at and below this point, or even a third of the values are at and below this point. It's slightly more than a third, but 35%, slightly more than a third, but slightly more than a third of the values are at and below 4. If I asked you a question like 75%, at least 75% of the values are at and below what point? Well, 75 is between these two, so you'd say 75% of the values are at and below 7. So this is your frequency distribution chart. And your frequency distribution chart is handy. I'm going to come back to why we use relative frequencies and cumulative frequencies, and why we use percents, stuff like that in just a second. But before I get to that, let me actually look at a different way to do this, because in this case, we've got 11 values technically. We're going between 0 and 10. We've got 11 values. What if you've got 100 values here? Doing a chart like this is impractical if you've got that many values. So we don't do a chart exactly like this. We do it slightly different. We do instead what's called a grouped frequency distribution. In a group frequency distribution, when the values are so spread out, we end up with as many values that maybe have frequencies of 0. We get a chart that just is way too long. So instead, we group up some of the scores. We make the data more understandable, more interpretable. We create group frequencies rather than absolute frequencies, rather than absolute values, rather than each value being independent and having its own category. We take and group sets of values together into one category or group. So in this case, and another way to say it is one class. A class is defined as a mutually exclusive category which represents elements or data points that share common characteristics. So we group observations that are similar to one another in value. There's a term here, mutually exclusive. Mutually exclusive means each data point can only be in one category. We'll come back to this later, but when we're doing group frequency distributions, it needs to be mutually exclusive, meaning there can be no X value that's in more than one category. It also should be exhaustive, meaning all X values are in a category. But that by the way we're going to set it up, it comes to that. Okay, so how do you set up a group frequency distribution? So the first thing you do is you take the highest score minus the lowest score. And let's say we've got a theoretical distribution. I'm going to give an example on the next slide, but I'll write up an example on this. Let's say we've got a theoretical distribution where the highest value is a 52 and the lowest value is a 31. So the first thing you do is you take the highest value, subtract the lowest value. So 52 minus 31, we get a score of 21. Then we add 1, so we're getting 22. 22 is our number of interest that we're looking at here. And 22 is essentially going to be our range of scores. From here, we're going to take that and divide by the number of intervals we wish to use. And I have an important note here, and this may take trial and error. This is not an exact science. This is where maybe you want 5 intervals, but you go and do it and you find out it doesn't work out that well. So you then do 6 intervals or 4 intervals. It might take a little bit of trial to do a couple different ones. Anytime I ask you on the homework or the exam, I'm going to tell you how many intervals I want. But if you're doing this yourself in your data and your research, then you may have to, in that case, decide yourself how many intervals you want. But let's say we've got this over here and we actually want 5 intervals. So we're going to take that number and divide by 5. And we get a value of, what is this, 4.4. Now we're actually going to take and round that up. So if we had class limits, if we had things where we're looking at the different true limits, then that would come in here, but if needed, we're not going to deal with that here. But so we've got this 5. We're actually going to now round it up, or we've got 4.4, we're going to round it up to 5. So our interval length is going to be 5. The size of the class interval, or I, is going to be equal to 5. We've got 5 intervals that in each interval is of 5 length. So how we start this is we go to the lower limit. So the lower limit we set first. We take and look at the lowest number in the data set. And is that lowest number divisible by our I? Is that lower number divisible by 5? No, it's not. It's not divisible to be exact, to be a whole number. So instead we're going to round down. We're going to go down to the next lowest number below it, our lower level, that is divisible by 5. So in this case, we go down to 30. So our lowest interval, our smallest interval is going to start at 30. And then from there, we count up a number equal to our interval. So we've got 30, 31, 32, 33, and 34. So we've got 30 through 34 is our first interval. Our next interval starts with the next value, which is 35. We add 4 to that. We're going through 39. Then we've got 40 through 44. We add 5 to that. 45 through 49. And then finally, and I'm going to have to write it off to the side, 50 through 54. And you see we ended up with 5 different intervals. Each of them is 5 wide. And it includes all values because the highest value in the data set is 52. It's within the last group. The lowest value is 31. It's within the first group. And again, this is something that is subject to trial and error. Maybe you want your values to end on 5s on whole numbers, on multiples of 5. So instead, in that case, instead of doing the 30 to 34, you do the 31 through 35, then 36 through 40, all the way to 51 through 55. In that case, that is fine. Again, there's no definitive right and wrong answer here, as long as your lowest interval includes your lowest value and your highest interval includes your highest value. And sometimes by doing this, you may end up with more intervals than you intended. You wanted 5 intervals, but you may end up with 6. That is perfectly fine as well. After you've got your intervals, then you take the frequencies, just like we did with the frequency distribution, except instead you add up tallies for each interval. Make sure your total adds up to the number of data points that you have. But in this case, you would add up your frequency. Your f of x would be all values that are between 30 and 34. This one, all values between 35 and 39, that type of thing. On the next slide, I've got a graph of that. Let's look at that real quick. Now, this is different values than what we just talked about. This would be exam scores. It's a little bit messed up in that the top interval here has 11 data points possible. So you can see here it's not exact. But that is one thing that can happen with group frequency distributions. The point is all the ones in the middle should be the exact same size. The one at the bottom, actually, in this case, sometimes with group frequency distributions, instead of the one here being 30 to 39, it'll be 39 and below. So everything at 39 and below. So sometimes group frequency distributions don't have the same size. You could change this up to make it so all of them were the same size by doing 31 through 39, 31 through 40, 41 through 50, 51 through 60, all the way up to 91 through 100. And that way each of them have 10 values. Just trying to show here that there is different things that can come into play that could, it's not exact is what I'm trying to get at. You could have different things that come into play that make it so you get these small discrepancies. That being said, what you're seeing here, important to note that it is mutually exclusive. The groups are mutually exclusive. That is, like, a value is not going to be in two different groups. You don't have this one here going to 70 and this one also including 70, so that 70 would be in both groups. What you've got here is your frequencies at each interval. So there are 12 that have between 90 and 100. One that's between 30 and 39. This is actually those graphs that you saw for the histogram earlier. And just like with a regular frequency distribution, you've got cumulative frequency, relative frequency, cumulative relative frequency, percent, and cumulative percent. Now, I said I'd come back to this because this is an important point that does need to be made. And that is, why do we convert frequencies to proportions or percentages? And this is probably the most important thing when it comes to frequency distributions. Why do we convert these? Let's think about it for just a second. But why do we have, instead of dealing with an f of x equal to 5, y is a relative f of x that's equal to 0.05, or a percent that's equal to 5%. Why are these more important than this? Why is a relative frequency and a percent more important than a frequency? And that is because comparison reasons. If I had two data sets, if I had two groups, and I asked basically in one group, I asked how, yes or no, are you male or female? That easier way to say it. Just go back to saying the number of males in a group. And we collect data on 100 people, and it turns out 50 of them are male. So in this case, our f of x is going to be equal to 50. Our frequency is 50. However, our relative f of x This is where we take that 50 and divide by the total, the n, the 100. The n is 100. If we take our relative f of x, in this case, we're getting 0.5. And our percentage is equal to 50%. So let's ignore these values for a second and just look at these values here. So we've got 50 males. However, let's say I got another group. And in this group, I take and ask 1,000 people. But in this group, I get 400 males. Is basically the second group that I collected, is it more likely to be male in that group than it is in the first group? Because if you look at this, our n equals 1,000, our f of x equals 400, so our f of x down here, I just wrote it up there, but our f of x is 400. In this case, we've got 400 males. In this case, we've only got 50. If we just used frequencies, we would look at this one and say, well, males are more likely in this group because there's 400 in this group and 50 in this group. So group 1 and group 2. But that's not the case. It's not more likely to be male. Yeah, there's more males in that group, but there's only more males in that group because we collected data on more people. If we convert this then instead to a relative frequency, we would take, and it would be equal to our frequency of male divided by our n, which is 1,000, or it would be 0.4. So now we can even see this 0.5 here is greater than the 0.4 here. But if we convert it to a percent, we get 40%. We can therefore see I used easy numbers because I divided by 100 and 1,000. But if you don't have easy numbers, it comes in handy. But 40% in this group are male, 50% in this group are male. Therefore, it's more likely to be male in group 1 than it is to be male in group 2. So going back, long story short, I got long-winded there, but why do we use proportions? Why do we use relative frequency? Why do we use percentages? Because if we're going to make comparisons between groups, we have to use that. You cannot use absolute frequencies when making comparisons between groups. Okay, thank you. Come on back.